Hello, everyone. Thanks for joining today. It's the second webinar of a series of 5 webinars we just started 2 weeks ago. I'm part of Greenflex, which is the coordinator of the 3D project communication and which is organizing this series of webinars. Today, we're going to have Benoit from Axens that will present the DMX process, which is an innovation from the 3D project. We're going to explain how it was developed, what are the advantages, and why it is different from the other processes that maybe you might know. So don't hesitate to ask questions if you have some on the tab at the bottom of your screen. You can also use the chat to ask question about the presentation, something that is not working. I will answer that. And at the end of the presentation, we will answer the questions. So we also have Clément from Axens and Vanya from EFPN that will be able to answer all of your questions. The presentation is recorded, so we will share the replay on our LinkedIn page, so you can follow us here to have more information and to know more also about the next webinars we will have. So thank you, and Benoit, it's yours.
Thank you, Ludivine, for the introduction. I'm very pleased to be with you today and to have the opportunity to present you more in detail the process aspect of DMX, our carbon capture process, and the demonstration unit we have in Dunkirk. So I'm Benoit Louis. I work in Axens as a technology engineer specialized in carbon capture. So few words about Axens. We are a subsidiary of IFPN. We are international group. We sell catalyst, adsorbent, equipment such as heaters and modular units. We are also licensor. Historically, we are involved in domains such as oil refining, petrochemistry, but we are also involved in new domains such as plastic recycling, carbon capture, water and air treatment. So Axens is born from the fusion of two entities, Procatalyze and the industrial division of IFPN. But what is of interest on this slide is the acquisition of Prozernat in 2017. So Prozernat is a historic licensor involved in gas treatment, and with this acquisition, Axens has acquired all the portfolio of natural gas treatment. So now in Axens, we are involved in gas drying, gas purification, sulfur recovery units. But what is of interest for us today is gas sweetening. So we provide license on a mine-based unit. So for the story, everything started 60 years ago on a plant located in Lac. It's in the south of France. So this plant was operated by Total. It was a very acid gas coming from this plant. So a technology has to be developed to tackle this subject, to capture the high amount of H2S in the natural gas. So the mine is born. It's a mine-based unit using a basic solvent which can attract the acid components such as H2S or CO2. And this led a lot of improvement on the solvent formulation, on the process optimization has been made. And we have a lot of units in operation. We have a lot of background of designing such units. But the mine is well adapted to capture acidic components on high pressure gas, such as natural gas or biogas. But it's not the case when we speak about industrial flue gas, because this gas are at atmospheric pressure. So we developed a new process for post-combustion application. The name of this process is DMX. The name of the process is also the name of the solvent, which is basically a mix of different amines diluted in water. So some of you may be familiar with this type of simplified diagram of a mine unit, but let's have a look on it to see what is the main difference between a first generation classic mine unit and the DMX. So we have a flue gas coming from industry. It's considered well pretreated in terms of temperature because absorption is performed at low temperature around 40 degrees. In terms of pressure, we have to increase a little the pressure of the flue gas to overcome the pressure losses inside the absorber in terms of level of impurities. So the flue gas is routed to the DMX. It contains a certain percentage of CO2, which has to be removed. At the top of the absorber, we inject the lean solvent, the lean DMX, and the solvent, which is basic, can attract the CO2. And finally, the flue gas is backwashed with this solvent. So at the top of the absorber, we recover a gas treated, purified without CO2. And the CO2 is all concentrated in the rich solvent, which has to be regenerated. So the rich solvent is routed to a regeneration section composed of a stripper. So we regenerate thermally the solution. We inject energy with the reboiler. And at the top of this column, we recover a pure CO2 stream. It's saturated in water. And at the bottom of the column, we have the regenerated solvent, which can be routed back to the absorption section. So you have to note that this reboiler is the main energy consumption of the unit. So we have to optimize this energy consumption to make the carbon capture process the more efficient possible. So what is the main difference between our DMX and a basic mine unit? It's this vessel in the middle of the diagram. It's the decanter. Because under certain conditions of temperature and CO2 concentration, the solvent is demixing between two liquid phases. And one of these liquid phase is free of CO2. Finally, it has been automatically regenerated because of the physical properties of the solvent. So we can mix back this automatically regenerated phase in the lean solvent phase. All the CO2 is concentrated in the other phase. So finally, we make advantage of this demixing capability, and we can reduce the amount of solvent to be regenerated inside the stripper. So we can reduce the size of the unit and the energy penalty of the unit. Not that the DMX has a high capacity, which means that when we compare it to a first generation solvent such as MEA, which is a common benchmark, we need less solvent to capture the same amount of CO2 with DMX. So we claim to have low reboiling duty between 2.3 to 2.9 gigajoule per ton of CO2. It depends on the application from the industry where the flue gas is coming. So the more CO2 is concentrated inside the flue gas, the easier is the absorption. So we have lower reboiling duty at the end. Another very important point is that the DMX is thermally stable, which means that we can operate the stripper at high temperature, so at high pressure, and we can recover CO2 at high pressure. So at the end, we can save up to one stage of compression. We can save a lot of electricity for the conditioning section. And it's low sensitive to oxygen, so we have less degradation and less makeup is required. So DMX process, it's a very versatile process. We can apply the DMX to a lot of different applications. It may be on a steel aluminum plant, cement plant, incinerator, coal or gas power stations. We can treat a wide range of CO2 concentration from 2 or 3% of CO2 to 25, 30%, a wide range of flow rates. Now, let's talk about the 3D project. It's a project involving a lot of different partners, such as European Union, ArcelorMittal, IFPEN, Total. So first aim of this project is to validate the DMX by building and operating a demonstrator plant at pre-industrial scale. So 0.5 ton of CO2 are captured per hour. So the module has been started up, is located in ArcelorMittal plant in north of France. The operation will last less than 2 years. And at the end, the aim is to validate and commercialize the technology by the end of this year in 2023. And there is a second phase of this project, is a full pre-FEED study on the full carbon capture chain. On the same application case on ArcelorMittal steel mill plant, but this time to treat 1 million tons of CO2 per year. And this study is not only focused on the carbon capture unit, of course it will be done with DMX technology, but we are also having a look at what's next to the carbon capture unit. So the heat recovery from the steel mill plant, the CO2 conditioning, liquefaction, transportation, storage. And the global aim is to have a global view of what a carbon capture project looks like. So in this part of the 3D project, we have been involved in the carbon capture section with the DMX technology. So we have provided a lot of different documents, such as the heat and material balance, the main equipment, process datasheets, PIDs with information about the material, about the line sizing, the security of the process, utility consumption, and class 4 capex. So we are able to give this information on the DMX project. Now let's focus on the demonstration. So for the context, as I said, it's located in Dunkirk on a ArcelorMittal plant. So we pick a small amount of the blast furnace gas network of the ArcelorMittal plant. So the typical composition of the blast furnace network is this one. So we have a big amount of CO2, 25%. Something is particular with this case because cement plant operation is under reductive atmosphere. So finally, at the end, we have a lot of carbon monoxide in the flue gas. We have hydrogen. We have a low content of oxygen, which is not really which is not common when we treat flue gas from other industry. But it's not a problem for the DMX because carbon monoxide and hydrogen are not co-absorbed by the solvent. Now for the demonstrator process flow diagram, you will recognize the absorption section with the absorber, the regeneration section with the regenerator, the decanter section with the decanter. Here you have the line with the free of CO2 phase, which has been demixed and routed back to the lean solvent loop. What is of interest in the process flow diagram? So first on the absorption section, we have a water wash section to limit the solvent emission. So it's a recirculation of water. The aim is to wash the gaseous effluent. We have a solvent intercooling section. So why a solvent intercooling section? Because absorption is an exothermic reaction. So when we absorb the CO2, the temperature is increased, so solvent temperature is increased, but the CO2 absorption is favored at low temperature. So in the middle of the column, we draw off the full quantity of solvent and we cool it down to the temperature is decreased and the absorption capability of the solvent is increased again. And we re-inject all the solvent in the low section, in the bottom section of the column. We also have a gas conditioning section. It's possible to vary the pressure and flow rate of the flue gas. We have a filtration section in this package too. Here you have a lean rich solvent heat recovery. It's something really common in a mine unit. So we recover the energy from the regenerated solvent loop, and we send this energy to the rich solvent loop. Note that the reboiler is supplied with MP steam, and the MP steam is recovered from the ArcelorMittal plant directly. Last, we have two recycle lines. One of the CO2 capture. We can recycle this CO2 and re-inject this CO2 at the inlet. Same for the treated gas. And why these lines? To make possible to vary the composition of the feed flue gas. So we can vary the CO2 concentration. We can test different CO2 concentration. So key figures of this demonstrator: maximum height is 26 meters due to the absorber column. So 5 persons are here to operate the DMX. It constitutes of 3 columns, so 2 absorbers. Finally, the absorber has to be split into 2 columns to respect a maximum height. And what is really important is that it's a well-controlled and well-instrumentalized unit. We have a lot of sampling points, a lot of online gas analysis, a lot of control instrument, alarm, control loop, because we want to know everything about the process, to validate our technology, to make a heat and material balance, to validate our model. For the capacity of the unit, we have a 10 cubic meter of solvent inventory. We capture 0.5 ton of CO2 per hour. The CO2 capture rate, it's from 90 up to 99%. Depending on the CO2 concentration at the inlet, it's possible to vary this concentration thanks to the recycle lines. It's possible also to vary the pressure at different spots of the unit and temperature to make a lot of different tests. The 3D model, so what is important here is the column section with the regenerator and the 2 absorbers. Here it's a decanter section, and very important location, the analysis shelter and the control room. So the first results, the demonstrator has been started up in October in 2022. It has been stabilized. The unit is operated a full day, full week, and we have achieved the CO2 capture of 0.5 ton of CO2 per hour. We have no solvent degradation, no foaming tendency, and the solvent is demixing as expected, as simulated. So it's fully validated. We have 80% of solvent rate of demiction. This phase has not to be regenerated thermally, so it's fully validated. The decantation. Here it's a photo of the decanter from the demonstrator. Okay, so now what we want to do with this demonstrator. So first, during 8 months, we want to do a parametric test campaign. So what are the objectives and the different type of tests we want to do on the demonstrator? We want to test and to validate the energy penalty, our model of simulation, on the absorption, the unit flexibility, capacity, also the good operation of the DMX unit. We want to validate it, and we want to assess the good solvent emission management. So it's possible, thanks to the recycle lines, to vary the CO2 concentration at the inlet of the DMX unit. And we want to reconstitute different feed flue gas to assess different real application. So the base case would be, of course, the blast furnace flue gas from ArcelorMittal, but we want to reconstitute a coal-fired power station gas, a natural gas power station feed flue gas too. So what are the challenges of this demonstration? First, the most important is to validate the energy penalty reduction. Okay, it will depend a lot of the CO2 capture application. The more is the CO2 concentrated, the easier is the absorption. But what is important is to compare the energy penalty of DMX with the benchmark solvent. So we choose MEA because it's very well documented, and we are expecting around 30% reduction depending on the application case in terms of reduction of energy penalty. And to do that, we'll be able to produce a lot of different heat and material balances because of the lot of sampling point analysis, follow-up of the units. We also want to assess the goods emission management. So why do you want to reduce the solvent emission at the top of the unit in the effluent gaseous effluent? First, for environmental purpose, because we don't want to reject a chemical product at the top of our units, and also for solvent inventory management, because if we lose solvent because of volatility, solvent inventory will decrease, concentration of a mine will decrease, and at the end, we lose a good absorption capacity of the solvent, and we have to do makeup. So it's important to manage these emissions. So to do this, we have a water wash section at the top of the absorber with demister. So this section is to tackle the evaporation and liquid entrainment problems. And we have feed gas filters to reduce aerosol formation because they are mainly due to the particles that are present in feed flue gas. So we'll do a lot of specific campaigns, and this solvent emission will be monitored by infrared analysis. And we also will have a look to the volatile organic component emissions due to solvent degradation, and also it will be monitored by FTIR. After that, we'll do a long-term test, duration 6 months. So this test aim is to prove the good stability of DMX solvent over a long-term period of operation. So the good functioning of the unit under different temperature, pressure, and the good solvent stability. So we will have a look at the degradation of the solvent, at the emissions of the solvent, the corrosion in the unit. So I've talked a lot about the analytical methods to follow the units. So we'll have a gas chromatography, ion chromatography, and optical emission spectrometry with infrared, for example. So to conclude, we have built and started up a demonstrator located in Dunkirk. The nominal capacity is 0.5 ton of CO2, and the aim is to fully validate the technology. And the goal, commercializing DMX by the end of this year in 2023. It will be operated less than 2 years, and we will test a lot of different carbon capture scenario, carbon capture applications. And we'll do a lot of specific tests, of course, to optimize our model of simulation, to enhance our model of prediction and simulation, to assess the limitation, solvent emission limitation section we implemented in our unit, and to optimize the energy penalty. So to do that, we have a lot of instrumentation and analytical follow-up on the unit. So thank you. So this project is funded by European Union, and for the operation of demonstrator is supported by ADEME.